we got section 2.3, double angle, power reducing, and half angle formulas. Essentially, we are sort of continuing the theme from 2.2, and we're going to keep looking at the formula sheet, all those. I mean, it looks like a crazy amount of formulas on that sheet, you know, there's a lot of them. I don't have them all fully memorized. I don't expect you, like I said probably in class, and I said in the last video, I don't expect you to memorize all these formulas, but because you'll have the sheet on the test, but you still should become really familiar with them in order to be fully successful. And let's see how we're going to use these formulas. If you look at your formula sheet, I don't know if we're on the back of the paper yet, but we might be at the bottom of the front side, or maybe we're on the back. Anyway, double angle formula, shouldn't be that tough to find it. The double angle formulas basically, for example, say this. If you have some angle x, and you're doing the sine of 2x, like that's why we call it a double angle, we can just, like we know that someone at some point figured out that this would be equal to 2 times the sine of that angle x times the cosine of x. So in example 1, they're saying, okay, so if the sine of theta is 5/13, and theta lies in quadrant 2, find the exact value of the following. And let's start with the sine of 2 theta. Well, like I said probably in class and in the last video, doesn't matter what variable this is, if it's an x, if it's a theta, if it's a alpha, doesn't matter. So when you look at this, again, this is why I say over and over again, you don't need to memorize the formula sheet, but because you don't have to, because you'll have it. But I mean, you should be able to become familiar enough with it where you look at this and go, hey, that's a formula. Sine of 2 theta. I don't know exactly maybe what the formula is, but I know that's a formula. And so you look at your sheet and you go, well, this is going to be equal to this. 2 times the sine of alpha times the cosine, or sorry, I said alpha, theta. 2 times the sine of theta, cosine of theta. Well, what do we do from here? Well, maybe we know the sine of theta. We do. Maybe we know the cosine of theta. We don't, but we can figure it out. Wow. This might be going slightly out of order in a way. But we did a problem like this last section where we used skills and knowledge that we acquired last unit to figure out the cosine of theta. Like, what's the cosine of theta? Well, we need to go down here and figure out what x is. Because again, from here, you know that y is 5 and r is 13, and so you put those into the Pythagorean theorem. Again, dot, I mean, we've done this 100 times. So you should know the procedure by now of given y and given r in this context, you can figure out x is -12. Why negative? Because all of these details matter. We're in quadrant 2, and so x is -12. So that makes cosine -12 over 13. Which means we can, again, this is sort of out of order a little bit, I guess, as far as the steps, I guess. But so this goes back up into here, and now we can fully plug into this where it's 2 times 5/13 times -12/13. You clean that up, and this is our final answer. So we're using old tricks, but we're applying a new formula, a double angle formula. Now we want to do the cosine of 2. Ooh, this is interesting. Here we go. Now we can see it right there. Check it out. So the cosine of 2 theta, our formula sheet says, like, if we have a double angle for the cosine, it could be equivalent, it could be equal to this. You know, so again, theta is like our x, it doesn't matter. So cosine squared of the angle minus sine squared slash, or this is also equivalent, I guess, like over here, or 1 minus 2 sine squared of x. Now, I actually remember, legitimately, you know, no exaggeration, I remember being your age in high school thinking, why is there 3? And more importantly, why is there 3? And more importantly, like, which one do I use? Like, which one is the one? Well, there's actually a pretty silly or cheap answer to that. I mean, it doesn't matter. I don't really know for sure why textbooks tend to give 3 versions of it, because this and this and this are all, they're all the same. You know, it would take very, 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 very few steps of work to just prove and verify that this is the same as this, which is the same as this. They're all basically the same. So in a way, it doesn't even matter which one you pick. But let's pick the first one. So put your fears to bed, okay? They're all the same. Don't stress out over which one is the bestest one. So anyway, so we take cosine of 2 theta and we rewrite it like that. And since we now know from before, like, not only do we know the sine of theta is 5/13, we now know that the cosine of theta is negative 12. Well, actually, ooh, you know what? It might be for the best, or like correct, to say that's theta. Possible bonus point I would give you in class if you notice that before I do. But yeah, so the cosine, we know the cosine of theta is negative 12/13. And so plugging into this is, you know, automatic. So the cosine squared becomes this squared. The sine squared of theta becomes this squared. How do you square a fraction? I really hope this doesn't trip you up. This is like something you should be familiar with based on your past, your dark and mysterious math past. And so it'd be positive 144 over 169. Over here you get this. And then you probably would go ahead and subtract those fractions. Pretty simple because they already have the same denominator. And so your final answer for part B here is that. What about the tangent of 2 theta? Well, that directly refers to a formula on our formula sheet as well. So this would be equal to the 2 times the tangent of theta all over 1 minus the tangent squared of theta, right? So, well, x slash theta. Hey, you know what? I'd give you a bonus point for pointing this out. Technically, since this is theta, these should be thetas, yeah. So, okay, what the heck is the tangent of theta? In fact, just how did I know the tangent of theta is negative 5 over 12? Well, remember, people, like, we've always known that y was 5, that r was 13. We figured out that x was negative 12. And so, I mean, wait, we still have to know that the tangent is y over x? Yep. So we just put y over x, and negative 12, so we plug it in. And now we just take this monster and clean it up a little bit. You can do 2 times this fraction. You can do this fraction squared, and then eventually we're going to subtract. So we didn't subtract yet, but 2 times negative 5/12 gets you this. I hope working with fractions is still not something that is totally like a speed bump, like throwing a wrench into the gears. I mean, come on. Understand fractions, people. This gets you that. When you square this fraction, you get 25 over 144. Now, in order to keep cleaning this up, to get to like a final answer, we're going to do this subtraction. How do I do 1, or in other words, 1 over 1 minus that fraction? Well, you would, I guess the work is not shown here, what's going on behind the scenes. But 1 over 1, if you gave them common denominators, this would become 144 over 144. And then you could subtract to get 119. All right, now, once again, how do we deal with this? We have a fraction divided by a fraction. Ooh, look, I even wrote it out for you. This is what's going on behind the scenes. Dividing by a fraction, you need to flip it, and it becomes a multiplication. So multiplying by the reciprocal is the same as dividing by it. And so multiplying fractions, I hope, is something that doesn't confuse you, and you end up with negative 120 over 119. Final answer. Second example. Find the exact value of that whole thing. Well, kind of like last section, sometimes you take, let me give you some perspective here. Never mind. I guess it wouldn't be that, I don't know if it would be that helpful as I would like. So let's just say this. You need to become familiar enough with the formulas where you look at this entire fraction and recognize it as, hey, 2 times this crazy fraction here, wasn't it like a formula somewhere? And then you look through your formula sheet and you might know exactly where to go. And I mean, look at this, and look at this. Okay? So we can totally recognize this as the right side of, the double angle formula for tangent, where x equals 15 degrees. And so we can take this and change it into this because they are equivalent. The formula says that this equals this. It's just turning the right side of a formula into the left side of the formula. Okay? And what was x? 15. Hopefully real quick, from here to here, it doesn't take you very long to go from there to there. It's the tangent of 30. Look at your cheat chart, and you're done. We can do the tangent of 30. So 15 degrees, not something we can work with. Not something on our cheat chart. But once we apply the formula switch, tangent 30, and that's the final answer from our sheet. Example 3. Okay, this is kind of what I was just thinking about. So Find the exact value of the cosine of 112.5 degrees. Obviously, the cosine of 112.5 degrees is not comparable to any right side of a formula on our formula sheet. So, but don't we sometimes use the left side and we make something comparable to a left side of a formula, or at least we can rewrite it as something very, very, very comparable to the left side of a formula. So this might be one of those situations. So, because you look at 112.5 degrees, that's not one of our nice angles, is it? Like thinking again back to Unit 1, 112.5 degrees. So we want to rewrite 112.5 as something else. You know, I'm thinking back to like last section. I mean, could we rewrite it as the sum of two angles? Could it be like a nice angle that we like plus another nice angle we like to take the place of 112.5? No. The difference of two nice angles we like? No. Thinking back to like these formulas, could we rewrite, what was it, sine? This was cosine. Could we rewrite 112.5 as 2 times a nice angle? Right? Because this angle x, like we want to be a nice angle. So could we rewrite 112.5 as 2 times something? Wouldn't it be like 2 times 56.25? No. But what if we look at the half angle formulas? That's also a thing. Okay? The half angle formulas. And what if we rewrote 112.5 as 225 divided by 2? Because 225 divided by 2 is the same as 112.5. And 225 is a nice angle that we like. Okay? So we can use the half angle formula for cosine and rewrite it like so. And what was our x? You know, it was 225. So once we convert it to the right side of this formula and we plug in our nice 225 for x, we can go with that, you know. We can proceed because we can do the cosine of 225. You look at your cheat chart and you see that the cosine of 225 is negative root 2 over 2. And so we do the cosine of 225, you know, to kind of get us going. And we get to here. All right? Now, the plus or minus out in front, that is something we have to deal with, for sure. Because it's going to be one or the other, right? We might deal with that at the end. But this is not something that we want to leave as like a final answer. We don't really like to have fractions within fractions, like fractions in our numerator, fractions in our denominator. And so what are we going to do to clean this up and fix this? Well, there's a couple different ways to do it, but what I am going to do is multiply the entire top of this fraction by 2 and the entire bottom of the fraction by 2. You're allowed to do this. And now the bottom just becomes 4. And on the top here, we are distributing. And so 2 times 1 is 2. And then when I multiply 2 to this fraction, the 2's cancel out, and I'm left with negative root 2. Replay what I just said. I mean, it's a video after all, isn't it? Feel free to replay that as many times as you need. But, I mean, I'll just say it again right now. 2 times 1 gets you this 2. 2 times this fraction, the 2's would cancel, and you'd get this. So where do we go from there? Where we go from there is, I think we realize that this entire square root of the entire fraction can be broken up, and we can take the square root of the numerator and denominator separately. And if you take the square root of the bottom, you can simplify that. That's just like, what's the square root of 4? It's just going to be 2. So there's nothing we can really do on the top. I'll say that again. There's nothing we can really do on the top with the square root. That's going to remain the square root of 2 minus root 2. But the bottom square root of 4, that's just 2. Okay. Now I think I'm going to, even though we could have dealt with this much earlier, let's deal with the whole plus or minus thing. Which one is it? Right? The cosine of 112.5 degrees was always going to be, what, positive or negative? Because don't forget, like, this is what we're doing. We're finding the value, the exact value, of the cosine of 112.5. Positive or negative, people? 112.5 degrees is in quadrant 2. So the cosine of it was always going to be negative. You could have answered that question all the way at the start of this problem, that it was always going to be negative because of, it's 112.5 degrees. So it depends on the quadrant, just like we've been talking about since last unit. Example 4. Okay, example 4 is kind of a can of worms. The directions say, write an equivalent expression for cosine to the 4th power of x that does not contain powers of trig functions greater than 1. So looking at your formula sheet, people, what formulas do you think, or what formula do you think applies to this situation based on what those directions say? Take a wild, stinking guess. Look at your formula sheet. Which formula do you think we're going to use? Because this has a power of 4, and we want to rewrite it to where, like, there's no powers greater than 1. Well, there's these things called the power-reducing formulas, where the cosine to the 2nd power of x, or of something, you can rewrite as that, because it's equal to that. See how there's no, powers over here greater than 1? So these formulas allow you to go from something that has a power 2, and it reduces the power. Okay? Now, our first, I guess, potential speed bump here is that, well, this says cosine squared is that, but what about cosine to the 4th? What the heck can I do? Is there a formula for the cosine to the 4th power? Well, no, but couldn't we rewrite cosine to the 4th as cosine squared of x times cosine squared of x? Of course we can. So what we're going to do now is apply this formula to this guy and this guy. That's the strategy. And so we do it. 1 plus cosine of 2x all over 2 times 1 plus cosine of 2x all over 2. And we just roll with that. So what do you think we're going to do next? Because, we're not done. Because if I multiply what I have here together, fraction times fraction, the bottom is going to be 4. How do I do this numerator times this numerator? I FOIL, and I'm going to pat myself on the back here. I wrote out the entire result of FOIL. Firsts, outers, inners, last. This numerator as a quantity times this numerator as a quantity. You need to FOIL it out and do all that distributing. Oh, and look what I got here. Well, this term and this term combined together, they're like terms, but the big issue is that I have a power of 2. I'm not really supposed to have a power of 2 in my final answer, so here's what happens next, people. Like I said quickly, this term and this term are like terms. They combine to be that. All right? And then this guy, I need to apply the formula again. Okay? I need to apply the power reducing formula again, where it's just that now I already have a 2x right here, and so when I do 2 times whatever, it's going to be 2 times 2x. And so that's why I have a 4x, because whatever's here, I'm going to do 2 of that. Because here it'd be like next to 2x, but there's already a 2x here, and so it becomes 4x. Wow. And so now I get to there. And I guess the good news is there's no more worries about powers of 2 or more anymore. But we do have to clean this up, especially considering, well, maybe the only consideration is that we can have a fraction within a fraction. Come on, people. You know this. And so what I think I'm going to do is multiply the entire top and the entire bottom by 2. So 2 times 4 will just be... Oops, what the heck am I doing, man? I hope I didn't make a mistake. What's over here? Huh. Well, let me look at this again, because this should be an 8, you idiot. Pen. All right. I just threw myself there a little bit, because 2 times 4, that would be 8. And then when we do, okay, so once again, 2 times 4 is 8. And then this 2 gets distributed to all this stuff. So 2 times 1 is 2. Follow along here. 2 times this term is 4 cosine of 2x. Because I'm just going to do this 2 times 2. And then when I multiply 2 times this fraction, this 2 will cancel with that 2, and I'll just be left with the 1 plus the cosine of 4x. So this orange step is really about what do I multiply by to make this denominator over here go away, cancel out. And so that's why it was 2 over 2, because I knew that would do the trick. That's what it would take in order to clear fractions within fractions. Because I don't want fractions within fractions. That's why I wasn't done in this blue step anyway. So, man, another potential bonus point for people. I'm just too generous, I guess. Or too much of an idiot. Anywho, so what happens from here? Well, I mean, there's not much point to these parentheses. It's just we're adding. So I think we're going to need to do the 2 plus the 1. All right? The 2 plus the 1 to get 3. And then the 4 times the 2 cosine 2x. There's nothing else to do, right? So I guess all we're doing is 2 plus 1 to make 3. And gosh darn it, looks like I need to fix that. Okay. Final answer, I hope. Example 5. Example 5. Oh, your favorite kind of problem. Verifying an identity. Well, same old kind of concept, except looks like we're going to be utilizing our other formulas. So I hope this sticks out like a sore thumb. And and look at this. Also this, the sine of 2 theta. You know, we should probably replace that weird thing with what it equals in the formulas. And then what do you think of, well, we'll get that in a second. So, looks like I just went with, because remember the cosine of 2 theta, that was the one where there was, for some weird reason, 3 different versions of it. And then the sine of 2 theta, or x, equals this. So, I just went with the first version, I guess. They're all the same. It doesn't matter. And how about the tangent? Didn't we like changing that to sine over cosine? You know, pretty much all the time. And so what do we do from here? Well, I mean, what is there to do over here? I mean, we probably want to clear. So this minus could probably get distributed. Yeah? So that's a little bit of progress. And then, you know, now what do we do? What can we do from here? Well, do you notice 1 minus cosine squared is a direct, directly connected to the Pythagorean identities? And this 1 minus cosine squared of theta can be replaced with what? Sine squared. Because 1 minus cosine squared equals sine squared. And you know what? I just remembered in 2018, we're doing this kind of stuff. Oh my goodness. And so jeez. So, now it looks like some of my an earlier video might be a little bit incomplete, but hopefully in class I remember that that's now a thing, like that I'm just starting to do in 2018 for the first time, is utilize these codes to justify each step. Like, how did I go from this step to this step? Well, I applied the Pythagorean identity, you know. How did I go from, this step to this step? We multiplied, or we distributed the negative sign. Or how did we even get to this step? Quotient identity, and then we also applied the double angle identities or formulas, you know what I mean? So, anywho, from here, what can we do from here? Now the top says sine squared of theta plus sine squared of theta. Those are like terms, people. So those are like terms that combine to become 2 sine squared of theta. And then where does that go from there? Well, I guess I didn't have the room. Did I continue it here? No, I did not. So what happens from here? Now, well, I forget the code. Is it LT for like terms? Anyway, small potatoes. In the next step, we are able to cancel this sign with one of the signs up here. And so we would be canceling CA and C to get a final answer. Oh, what the heck? Also this. The 2's cancel out. So same justification. And the final answer would be the final statement where the sine of theta over the cosine of theta equals sine of theta over the cosine of theta. So the next line of work would be the final one where we just say this equals itself, and the justification would have been cancel, C-A-N-C. Final example. Well, I mean, come on, people. This should stick out like a sore thumb, as you need to replace that with what it is in the formulas. This is a half angle formula. And so let's see, it's probably over here. Whoa. Another one where it's like we got this, or this, or this. I'm not going to use that one. I mean, look, it's nasty and it's got a plus or minus. So it looks like we're just using this one. I'm sure it doesn't matter that much, but so here we go. And then cosecant, we don't like those. And so, oh my goodness. Look at this. Look at what we have now. After a quick half-angle formula switch, and then this would be, I'm going to assume half-angle formula. Maybe that's even something we need to add to our list of codes. Half-angle formula. What else? Reciprocal or quotient? Both. Both. Reciprocal identity. Quotient identity, that's the justifications there, people. But then look at what we have now. Look at this over here. 2 fractions so that we want to subtract together that already have the same denominator. So, and then this, we can just leave it as is. And just like that was nice, we were done. So I'm pretty sure the code would be SF for subtracting fractions. And I think that does it.